Right now, astronauts aboard the International Space Station are losing bone mass at 1% per month. Their hearts are shrinking, their eyes are changing shape, their DNA is accumulating damage that cannot be fully repaired. We celebrate spaceflight as humanity's greatest achievement, but we rarely discuss the biological price attached to every hour spent beyond Earth. Space does not want us there, and our bodies know it. Scientists have calculated the point where cumulative damage becomes irreversible, where survival transforms into slow deterioration, where no engineering can overcome what biology demands. This is not about rockets or destinations. This is about when the human body reaches its absolute limit. If you enjoy understanding the true boundary of human survival in space, hit that like button and subscribe. Now, get yourself comfortable. Let's begin. The moment you leave Earth's atmosphere, something begins happening that you cannot see, cannot feel, and cannot stop. Particles smaller than atoms are passing through your body at nearly the speed of light. Each one carries enough energy to shatter DNA molecules inside your cells. You feel nothing. No pain signals warn you. No alarm sounds. No instrument on your wrist buzzes with danger. But deep within the nucleus of every cell in your body, the damage accumulates with mathematical certainty. This is radiation, and it represents the first insurmountable pillar of the biological survivability ceiling in space. Scientists at NASA have spent decades studying what happens to human tissue beyond Earth's protective magnetic field. The results paint a picture that should concern anyone who believes space travel is simply an engineering challenge waiting to be solved. Radiation damage is not a problem that better spacecraft can fix. It is not a puzzle that smarter mission planning can circumvent. It is a fundamental collision between the cosmic environment and the structure of human cells. The universe bombards everything within it, with particle radiation at intensities that human biology never evolved to withstand. Earth exists inside a protective bubble created by our planet's magnetic field. This magnetosphere extends tens of thousands of kilometers into space, deflecting the vast majority of charged particles streaming through our solar system. Without this invisible shield, life on Earth's surface would face constant bombardment by energetic particles capable of stripping electrons from atoms and breaking molecular bonds throughout living tissue. The particles that make it through the magnetosphere encounter another barrier in our atmosphere, which absorbs and scatters most of the remaining radiation before it reaches the surface. These two shields working together reduce surface radiation to levels hundreds of times lower than what exists in interplanetary space. Humans evolved inside this double shield. Our cells developed repair mechanisms calibrated for the minimal radiation dose that penetrates to ground level. These repair systems work continuously, fixing approximately 10,000 DNA lesions per cell per day caused by normal metabolic processes and background radiation. The systems are elegant, efficient, and entirely adequate for Earth conditions. They are catastrophically inadequate for space. Step outside these protections and everything changes. The space radiation environment consists of three primary components, each presenting unique challenges to human biology. Understanding these components reveals why the radiation problem cannot be engineered away, and why it forms a hard biological ceiling on human survival in space. Galactic cosmic rays originate from outside our solar system, produced by distant supernovae, neutron star collisions, and other violent cosmic events that occur throughout the galaxy. These particles have been accelerating through interstellar magnetic fields for millions of years, reaching energies that dwarf anything humans can produce in the most powerful particle accelerators ever built. The Large Hadron Collider accelerates protons to approximately 7 trillion electron volts. Galactic cosmic rays routinely arrive with energies exceeding 100 trillion electron volts, and the most energetic particles detected carry more than 10 million times that energy. Solar particle events erupt unpredictably from our Sun, releasing floods of protons and heavier ions that can arrive at a spacecraft within minutes of detection. These events correlate loosely with the 11-year solar cycle, but cannot be predicted with useful precision. A spacecraft crew might receive hours of warning before a major solar particle event, or they might receive minutes, or the event might occur while the Sun is on the opposite side of Earth and arrive without any warning at all. The intensity varies enormously between events. Some deposit trivial additional dose, others could deliver lethal exposure to unshielded humans within hours. Trapped radiation exists in belts surrounding Earth and other planets with magnetic fields, where charged particles become caught in magnetic field lines and accumulate to dangerous concentrations. The Van Allen belts around Earth contain protons and electrons at intensities that would quickly incapacitate unshielded astronauts. Spacecraft traveling to the Moon or beyond must pass through these belts, accumulating dose during transit. The Apollo missions minimized this exposure by choosing trajectories that passed through thinner regions of the belts, and by completing the transit quickly, but even these optimized paths delivered measurable radiation doses to astronauts. Galactic cosmic rays present the most persistent threat to long-duration missions. Unlike solar events, which occur sporadically, cosmic rays bombard spacecraft continuously at rates that vary only modestly with solar activity. During solar maximum, the Sun's expanded magnetic field provides slightly better shielding against galactic cosmic rays. During solar minimum, cosmic ray flux increases by roughly 20%. Neither condition provides adequate protection for human biology. These galactic particles include not just protons, but heavy ions such as carbon, oxygen, silicon, and iron nuclei, traveling at significant fractions of light speed. When such a particle passes through human tissue, it does not simply deposit energy and stop like a bullet embedding in a target. It creates a track of destruction through cells, breaking molecular bonds along a path that can extend through the entire body. A single iron nucleus traveling at 90% of light speed can damage or destroy every cell it passes through, leaving a trail of ionization that extends from entry point to exit. The ionization produced by a single heavy ion can sever both strands of a DNA double helix simultaneously. This type of damage, called a double-strand break, represents the most dangerous form of genetic injury. Your cells possess sophisticated repair mechanisms for single-strand breaks, using the intact complementary strand as a template to restore the original sequence with high fidelity. Double-strand breaks have no such template. The cell must attempt to rejoin severed ends without knowing what genetic information might have been lost or rearranged during the break. These repair attempts frequently introduce errors. Sections of DNA can be deleted entirely when the repair machinery cannot find the matching ends. Duplications occur when the wrong segments get joined together. Chromosomal rearrangements happen when breaks in different chromosomes get incorrectly rejoined, creating hybrid chromosomes with unpredictable consequences. The resulting mutations accumulate over time. Some mutations are harmless, occurring in non-coding regions or producing changes that do not affect protein function. Others disable tumor suppressor genes that normally prevent uncontrolled cell division. Still others activate oncogenes that drive cells toward cancerous transformation. The statistical relationship between radiation, exposure, and cancer risk has been established through decades of research, beginning with studies of atomic bomb survivors in Hiroshima and Nagasaki, and continuing through analysis of nuclear industry workers, uranium miners, medical radiation patients, and populations exposed to radioactive contamination. These studies consistently show dose-response relationships, where cancer incidence increases with cumulative radiation exposure. The relationship is not perfectly linear at all dose levels, but the overall pattern is unmistakable. More radiation means more cancer. Current estimates suggest that astronauts on a 3-year Mars mission would face cancer mortality risk increases of approximately 5% for males and 9% for females. The difference reflects baseline cancer rate differences between sexes and the greater radiosensitivity of breast and ovarian tissue. These figures represent statistical averages across populations with varying genetic backgrounds. Individual astronauts might experience far higher or lower risks depending on genetic factors affecting their cellular repair capacity. Some people carry genetic variants that enhance DNA repair efficiency. Others carry variants that impair it. But the population-level trend is clear. Extended exposure to space radiation increases cancer probability in ways that cannot be avoided through behavioral changes or mission planning. NASA maintains career radiation dose limits for astronauts designed to keep additional cancer mortality risk within acceptable bounds. The agency historically assigned different limits based on age and sex, ranging from roughly 180 to 700 millisieverts, reflecting differences in baseline cancer rates and remaining life expectancy. In 2021, NASA revised these standards to establish a universal 600 millisievert career limit for all astronauts, balancing equity concerns with radiation protection goals. These limits seem generous until you consider the radiation environment beyond low Earth orbit. The International Space Station orbits within Earth's magnetosphere, which blocks most galactic cosmic radiation and provides significant protection against solar events. The station's altitude of approximately 400 kilometers places it below the most intense regions of the Van Allen belts, while still within the magnetosphere's protective influence. Even so, astronauts on the station receive radiation doses roughly 50 to 70 times higher than people on Earth's surface. A 6-month mission to the station delivers approximately 100 millisieverts, compared to the 3 millisieverts that average Earth residents receive annually from all natural and medical sources combined. Longer missions to the station push astronauts toward their career limits faster than originally anticipated when those limits were set. Astronauts who complete multiple 6-month rotations may exhaust their career dose allowance before reaching the age when most professionals would consider retirement. The radiation environment, even in low Earth orbit, constrains how many missions an astronaut can fly and how long those missions can last. Missions beyond Earth's magnetic field would eliminate even this partial protection entirely. Astronauts traveling to the Moon or Mars would receive the full force of galactic cosmic radiation throughout their journey. Solar particle events would pose acute threats capable of delivering lethal doses within hours if astronauts could not reach shelter. The total mission dose for a Mars expedition would approach or exceed current career limits for most astronauts, concentrated into a single 2 to 3 year period rather than spread across multiple missions over many years. Shielding represents the most obvious potential countermeasure, and here the limitations of engineering become starkly apparent. Adding material between astronauts and the radiation environment can reduce exposure, but the physics of particle interactions create fundamental constraints that no amount of clever design can overcome. Light materials like polyethylene actually perform better than heavy metals for shielding against cosmic radiation. This counterintuitive result occurs because heavy atoms in metallic shields can fragment into secondary particles when struck by cosmic rays, potentially increasing the total radiation dose inside the spacecraft. An aluminum hull struck by an iron cosmic ray nucleus can produce a shower of secondary protons, neutrons, and nuclear fragments that deliver dose to astronauts, even though the original particle was stopped. Hydrogen-rich materials like plastics or water absorb energy more effectively without generating as many secondaries, because hydrogen nuclei are already the lightest possible fragments. But even optimal shielding materials provide only partial protection against the most energetic galactic cosmic rays. Calculations by NASA engineers show that realistic shield masses might reduce galactic cosmic radiation exposure by roughly 20 to 30% compared to a minimally shielded spacecraft. Achieving greater reductions would require adding so much shielding mass that spacecraft could never reach escape velocity with current propulsion technology. A shield capable of blocking 90% of cosmic radiation would need to be several meters thick, adding hundreds of tons to spacecraft mass that already pushes the limits of what existing rockets can lift. Active shielding concepts propose using magnetic or electric fields to deflect charged particles, mimicking Earth's magnetosphere on a smaller scale. These technologies remain theoretical for human spacecraft. The power requirements for generating fields strong enough to deflect high-energy cosmic rays would exceed anything current space power systems can provide by orders of magnitude. A magnetic field capable of deflecting particles with energies in the trillion electron-volt range would require superconducting coils larger than any ever constructed, powered by nuclear reactors more powerful than any ever flown in space. Even if such systems could be built, they would not stop neutral particles like the secondary neutrons produced when cosmic rays interact with spacecraft structures. This brings us back to the biological reality that defines the survivability ceiling. No amount of engineering changes the fundamental fact that human cells evolved to function within Earth's radiation environment. Space contains radiation intensities that exceed human cellular repair capacity when exposure continues over months and years. The repair mechanisms encoded in human DNA can handle Earth-level radiation doses indefinitely. They cannot keep pace with the damage rate in deep space. Research, published in peer-reviewed scientific journals, has revealed additional concerns beyond cancer risk. Studies of astronaut health data show evidence of accelerated cardiovascular aging associated with radiation exposure. The endothelial cells lining blood vessels appear particularly vulnerable to radiation damage. These cells normally maintain smooth vessel walls and regulate blood flow. Radiation damage causes them to become dysfunctional, promoting inflammation and the accumulation of arterial plaques. Over time, this damage contributes to atherosclerosis and increases heart disease risk through mechanisms distinct from normal aging. Astronauts who traveled beyond low Earth orbit during Apollo missions show higher rates of cardiovascular mortality than astronauts who remained in low orbit, though the small sample size limits statistical certainty. Only 24 humans have ever traveled beyond Earth's magnetosphere, and only 12 walked on the Moon. This tiny population makes it difficult to establish statistically significant differences in health outcomes. But the trend visible in available data matches what radiation biology would predict. Deep space travel accelerates cardiovascular aging in ways that accumulate over time. Neurological effects present another troubling dimension of the radiation threat. Animal studies using particle beams to simulate space radiation have documented persistent cognitive impairment following exposure. Mice show reduced performance on memory and learning tasks, with effects lasting long after radiation exposure ends. The particles appear to damage or destroy synapses in the hippocampus and prefrontal cortex, brain regions critical for memory formation, spatial reasoning, and executive function. The mechanism involves both direct damage to neurons and indirect effects mediated by inflammation. When heavy ions pass through brain tissue, they kill some cells outright and damage others in ways that trigger inflammatory responses. The resulting neuroinflammation can persist for months or years, continuing to impair cognitive function long after the radiation exposure ends. This chronic inflammation also appears to accelerate the accumulation of abnormal proteins associated with neurodegenerative diseases like Alzheimer's. Human data on neurological radiation effects remains limited because no one has yet spent extended periods beyond Earth's magnetosphere. The Apollo astronauts received their deep space radiation exposure during missions lasting less than 2 weeks. Whatever cognitive effects occurred would have been subtle and difficult to distinguish from normal variation in human performance, but the biological mechanisms involved apply equally to mouse neurons and human neurons. There is no reason to expect humans would prove resistant to damage that reliably impairs rodent cognition. The question is not whether space radiation damages human brains, but how much damage accumulates over mission durations measured in years rather than days. Solar particle events add unpredictability to the radiation threat. These events cannot be predicted more than hours in advance, and their intensity varies enormously from one event to the next. Space weather forecasting has improved over the decades, but it remains fundamentally limited by our incomplete understanding of the solar processes that trigger particle events. A moderate solar event might double the background radiation dose for a few hours or days. A severe event, like the August 1972 solar storm that occurred between Apollo 16 and Apollo 17, could deliver lethal doses to unshielded astronauts within hours. The 1972 event has become legendary in the space radiation community precisely because of its timing. Had that storm occurred a few months earlier or later, it would have caught an Apollo crew in transit between Earth and Moon, with only the thin walls of the command module between them and hundreds of rems of proton radiation. Mission planners acknowledged after the fact that such an event could have killed the crew before they could return to Earth. The astronauts got lucky. Future crews on longer missions cannot count on similar luck. Spacecraft on long-duration missions would need dedicated storm shelters where crew could gather during solar events. These shelters could use water tanks, food supplies, or specialized shielding materials to provide additional protection during the hours or days when solar particle flux remains elevated. But the need to shelter during solar storms adds operational complexity to missions and would interrupt activities during events lasting from hours to days. A crew on the Martian surface might need to abandon outdoor activities and crowd into a shelter with no warning, remaining there until the storm passes. The psychological burden of such events would compound the physical radiation exposure. The cumulative nature of radiation damage means that exposure history matters in ways that distinguish radiation from most other occupational hazards. Unlike many environmental exposures, where the body can recover if exposure stops, radiation damage to DNA is largely permanent. Damaged cells either repair imperfectly and continue dividing with altered genetic information, die through programmed cell death or necrosis, or persist in a senescent state that contributes to chronic inflammation and tissue dysfunction. Every hour spent in space adds to a running total of genetic damage that the body carries forward indefinitely. Scientists have proposed pharmaceutical countermeasures that might reduce radiation damage or enhance repair capacity. Antioxidants could theoretically neutralize some of the reactive oxygen species that radiation creates in tissue. DNA repair enhancers might help cells fix damage more accurately. Senolytics could eliminate damaged senescent cells before they contribute to cancer or chronic disease. Radioprotective drugs developed for nuclear warfare scenarios might reduce the immediate effects of acute exposure during solar particle events. None of these approaches has been proven effective for space radiation protection in humans. The energy levels involved in cosmic ray impacts far exceed what antioxidants can counteract. A single heavy ion creates a dense track of ionization that overwhelms any reasonable concentration of antioxidant molecules in the surrounding tissue. Enhancing DNA repair is vastly more difficult than suppressing a single metabolic pathway, because repair involves dozens of different protein complexes working in coordination across multiple biochemical systems. Eliminating senescent cells might prevent some cancers, while potentially accelerating others or impairing tissue maintenance functions that senescent cells support. The biochemistry of radiation damage and repair involves thousands of interacting molecular pathways, and interventions that help in one pathway often create problems in others. Decades of research into radioprotective drugs for military and medical applications have produced only modest improvements in acute radiation tolerance, and nothing that fundamentally changes the dose-response relationship between radiation exposure and long-term health consequences. This is where human biology, not technology, sets the boundary. Radiation exposure in space produces damage faster than human cells can repair it. That repair rate is encoded in our DNA, refined by billions of years of evolution under conditions that no longer apply once we leave Earth. The enzymes that recognize and repair DNA damage operate at speeds determined by protein structure and cellular biochemistry. No spacecraft design, no pharmaceutical intervention, no mission planning can change the fundamental mismatch between cosmic radiation intensity and human cellular repair capacity. The biological survivability ceiling exists because human bodies have finite tolerance for radiation damage. Beyond a certain cumulative dose, the statistical probability of serious health consequences becomes unacceptable by any reasonable standard. Beyond a higher dose, acute radiation syndrome produces immediate incapacitation through destruction of rapidly dividing cells in bone marrow and intestinal lining. The space environment delivers radiation continuously at rates that approach these limits within years rather than decades. For a mission lasting 3 years, the total radiation dose would likely fall between 800 and 1200 millisieverts, depending on shielding effectiveness and solar activity during the mission. This dose range exceeds career limits for most astronauts and enters territory where measurable increases in cancer mortality become statistically certain. It also enters territory where non-cancer effects like cardiovascular disease, cataracts, and cognitive impairment become significant concerns. Extending mission duration beyond 3 years proportionally increases dose and risk. A 10-year mission would push into dose ranges where acute effects might begin appearing in some individuals. The relationship is not perfectly linear because some damage mechanisms saturate at high doses, but the overall trend permits no escape. Longer missions mean more radiation. More radiation means more damage. More damage means closer approach to the biological ceiling beyond which survival becomes deterioration. Yet radiation represents only the first assault on human biology in space. Even if radiation could somehow be completely eliminated, even if scientists invented perfect shielding that blocked every cosmic ray and solar particle, other mechanisms would still impose strict limits on how long humans can survive beyond Earth. The next pillar of the survivability ceiling involves something equally inescapable and equally impossible to engineer around: the absence of gravity itself. Every second you spend in space, your skeleton is dissolving. Not metaphorically, not gradually in some abstract future sense. Right now, in measurable quantities, the mineral content of your bones is being reabsorbed into your bloodstream because your body has determined that structural support is no longer necessary. This process begins within hours of reaching orbit. It continues without pause for as long as you remain in microgravity, and its consequences extend far beyond weakened bones into every system that depends on skeletal integrity for protection and support. The human body is not a static structure. It exists in constant dynamic equilibrium, continuously rebuilding and reshaping itself in response to environmental demands. Your skeleton completely replaces itself approximately every 10 years through a process of constant remodeling. Old bone tissue gets broken down and absorbed while new bone tissue gets deposited in its place. This continuous renovation allows bones to repair microscopic damage, adapt to changing mechanical demands, and maintain strength appropriate for current loading conditions. Bones are living tissue containing 2 types of specialized cells locked in perpetual competition. Osteoblasts deposit new bone matrix, laying down collagen fibers that become mineralized with calcium and phosphate crystals. Osteoclasts break down existing bone, dissolving the mineral matrix and releasing its components back into the bloodstream. On Earth, mechanical loading from gravity and movement keeps these processes in balance. The weight-bearing stress of standing, walking, running, and moving signals bones to maintain strength sufficient for current demands. Bones respond to loading by becoming stronger. They respond to unloading by becoming weaker. Remove that gravitational loading, and the signals change dramatically. Bones no longer need to support body weight against Earth's constant downward pull. The osteoblast-osteoclast balance shifts decisively toward breakdown. Calcium and other minerals leach out of bone tissue at rates between 1% and 2% per month in weight-bearing bones like the spine, pelvis, and legs. This rate of loss exceeds what elderly osteoporosis patients experience by a factor of 10. Over a 6-month mission, astronauts can lose bone density equivalent to a decade of normal aging compressed into half a year. The precise mechanisms driving this accelerated loss involve complex signaling pathways that scientists are still working to fully understand. Mechanical stress normally triggers cells embedded within bone tissue to release chemical signals that promote bone formation. Without that stress, these signals decrease. Simultaneously, the absence of loading appears to increase signals that activate osteoclasts. The result is a metabolic imbalance where bone breakdown accelerates while bone formation slows, creating a widening gap between destruction and repair. This loss is not uniform across the skeleton. Bones that bear the most weight on Earth lose mass fastest in space. The lumbar vertebrae, which support the entire upper body when standing, show losses averaging 1 to 1.5% per month. The femoral neck, where the thigh bone meets the hip, shows particularly severe losses approaching 2% monthly. This region already represents a critical fracture risk for elderly people on Earth. Hip fractures kill approximately 20% of elderly patients within 1 year and leave many survivors permanently disabled. Astronauts returning from long missions carry skeleton structures weakened in exactly the locations most vulnerable to catastrophic failure. The trabecular bone inside these critical regions suffers disproportionate damage. Trabecular bone consists of a honeycomb-like network of thin struts that provide strength while minimizing weight. This architecture responds rapidly to loading changes, adding or removing struts based on mechanical demands. In microgravity, the body determines that many of these struts are unnecessary and dissolves them. Unlike the smooth outer cortical bone, trabecular architecture cannot simply regrow once destroyed. The struts that disappear in space may never fully return. Recovery after returning to Earth is incomplete and agonizingly slow. Some astronauts never fully recover the bone mass they lost. The mineral content may eventually return, but the microarchitecture of trabecular bone remains compromised. A bone that has regained its mineral density but lost its structural organization remains weaker than it was before spaceflight, more vulnerable to fracture under loads it would previously have handled easily. The longer the mission, the greater the loss, and the less complete the recovery. This relationship suggests a ceiling beyond which recovery becomes impossible. If astronauts lose enough bone mass during extended missions, the skeletal system may lack the biological capacity to rebuild what was lost. The body would reach a new equilibrium at lower bone density, permanently weakened compared to pre-flight condition. For missions lasting years rather than months, this cumulative skeletal damage might never fully heal regardless of how much time passes after return. Pharmaceutical interventions offer partial protection but cannot solve the fundamental problem. Bisphosphonates, drugs used to treat osteoporosis on Earth, can slow the rate of bone loss in space by inhibiting osteoclast activity. These drugs reduce the breakdown side of the equation without directly enhancing the formation side. Astronauts taking bisphosphonates still lose bone, just more slowly than they would without medication. The drugs also carry side effects, including gastrointestinal problems and, paradoxically, an increased risk of certain types of fractures with long-term use. Exercise countermeasures provide additional protection and have become central to long-duration spaceflight protocols. Astronauts on the International Space Station spend roughly 2 hours daily on specialized equipment designed to load bones and muscles against resistance. The Advanced Resistive Exercise device provides forces up to 600 pounds, allowing astronauts to perform squats, deadlifts, and other exercises that would normally require heavy weights. Treadmills equipped with harness systems pull astronauts toward the running surface, simulating some fraction of the impact forces that occur during Earth-based running. Cycle ergometers stress cardiovascular systems even without gravitational loading. This exercise regimen dominates the daily schedule on the space station. 2 hours of mandatory exercise represents more time than astronauts spend on most scientific experiments. The equipment requires constant maintenance, as intensive daily use wears components that would last years under normal conditions. Spare parts must be launched at significant expense. When exercise equipment breaks down, maintaining astronaut health becomes impossible until repairs are completed. Despite these heroic efforts, astronauts continue losing bone mass throughout their missions. The countermeasures reduce the rate of loss but cannot eliminate it. Studies comparing astronauts with optimal exercise compliance to those with less rigorous adherence show that exercise helps, but even the most dedicated exercisers return to Earth with measurably less bone than when they left. The microgravity environment simply does not provide the mechanical stimulus that bones need to maintain full strength. No exercise machine can perfectly replicate the constant loading that occurs during normal Earth activities. Walking delivers thousands of small impacts to leg bones daily. Standing requires continuous low-level muscle activation that loads the spine. Climbing stairs creates forces several times body weight through the hips and knees. Even sitting upright against gravity requires postural muscles to work constantly, loading the vertebrae they support. These mundane activities deliver signals that bones require to remain healthy. Muscle atrophy follows a similar pattern but progresses even faster than bone loss. Without gravity to work against, muscles have no reason to maintain their Earth-adapted strength. The body is metabolically expensive to maintain. Muscle tissue consumes calories even at rest. Evolution has programmed humans to shed unnecessary muscle mass whenever environmental conditions no longer require it. In microgravity, that programming activates with devastating speed. Postural muscles that normally work continuously to hold the body upright face almost no demand in microgravity. The erector spinae muscles running along the spine work constantly on Earth to prevent the torso from slumping forward. In space, there is no forward or down. These muscles can lose 20% of their mass within 2 weeks of spaceflight. The muscles of the lower back, essential for lifting and bending on Earth, atrophy. Similarly, astronauts returning from long missions frequently report lower back pain as weakened muscles struggle to support loads they handled easily before flight. Calf muscles that normally contract thousands of times daily during walking shrink measurably within the first week in orbit. The soleus muscle, the primary muscle used for standing, shows particularly severe losses because its function becomes almost entirely unnecessary in microgravity. Studies using magnetic resonance imaging have documented soleus volume reductions of 15 to 20% after 6 months in space, despite rigorous exercise countermeasures. The 2-hour daily exercise requirement reflects how seriously space agencies take this threat. Astronauts use resistance machines that provide loads comparable to weightlifting on Earth. They run on treadmills wearing harnesses that pull them toward the surface, with forces approaching body weight. They cycle on ergometers that stress cardiovascular systems even without gravitational loading. Every piece of equipment represents hard-won engineering, designed to fight the body's natural response to an unnatural environment. Despite these efforts, astronauts return to Earth measurably weaker than when they left. Rehabilitation after long missions requires weeks of physical therapy before astronauts can walk normally. Some struggle to stand immediately after landing, their leg muscles unable to support body weight that they could have carried easily before the mission. The combination of weakened muscles, altered balance systems, and cardiovascular deconditioning makes the transition back to gravity genuinely dangerous. Astronauts have collapsed attempting to walk after landing. Falls during the rehabilitation period pose serious injury risk to people whose bones have weakened along with their muscles. The heart itself changes in space, and these changes illustrate how deeply microgravity affects human physiology in ways that exercise cannot fully counter. On Earth, your heart pumps blood against gravity to reach your brain. The head sits roughly a foot above the heart, and blood must be pushed upward against that gravitational gradient with every beat. This requires constant effort that keeps cardiac muscle strong. The heart adapts to Earth conditions by developing enough power to maintain circulation regardless of body position. In microgravity, blood redistributes toward the head because gravity no longer pulls it toward the feet. Astronauts experience puffy faces and bird legs during their first days in space as fluid shifts upward. The heart experiences reduced workload because it no longer needs to pump against gravity. Like any muscle facing decreased demand, it begins to atrophy. The heart remodels itself for an environment where its Earth-adapted power is unnecessary. Studies using echocardiography show measurable reductions in heart mass during spaceflight. The left ventricle, the heart's main pumping chamber, becomes smaller and less muscular after weeks in microgravity. The muscular walls thin as cardiac tissue is reabsorbed. Cardiac output decreases as the smaller heart moves less blood with each beat. The heart becomes more spherical in shape rather than maintaining its elongated Earth-adapted geometry. A change that reduces pumping efficiency. These changes reduce the heart's ability to respond to sudden demands, a problem that becomes critical during re-entry and landing when gravitational forces return abruptly. An astronaut's atrophied heart must suddenly resume pumping blood upward against gravity, while simultaneously supporting the increased metabolic demands of a body under stress. Some astronauts experience dangerous drops in blood pressure upon return to gravity as their cardiovascular systems struggle to adapt. Cardiovascular deconditioning creates a cascade of related problems that compound each other. Blood volume decreases in space because the body interprets the headward fluid shift as excessive blood volume and triggers mechanisms to reduce it. Astronauts urinate more frequently in the first days of spaceflight, as their bodies shed what they perceive as surplus fluid. Total blood volume can decrease by 10 to 15% within the first week of a mission. This reduced blood volume contributes to orthostatic intolerance, the tendency to feel faint when standing up, which can persist for weeks after landing. Arterial walls also change in space in ways that resemble accelerated aging. Without the constant pressure cycling created by gravity-driven blood flow, changes between lying and standing, arteries become stiffer. The endothelial cells lining blood vessels function less effectively. Markers of arterial health, measured in astronauts after long missions, show changes that would normally take decades to develop on Earth. This arterial stiffening contributes to cardiovascular disease risk and may explain the elevated rates of heart problems observed in astronauts who traveled beyond low Earth orbit. Then, there are the eyes. Spaceflight-associated neuroocular syndrome represents one of the most concerning discoveries of the long-duration spaceflight era, a problem that emerged only as missions grew long enough to reveal it. Roughly 2/3 of astronauts who spend months on the space station experience measurable changes in their vision. For many, these changes are mild and reversible after return to Earth. For others, they result in permanent vision impairment that affects their ability to perform mission tasks and continues long after returning home. The syndrome involves multiple changes to eye structure that compound each other. The optic nerve becomes swollen as pressure increases in the cerebrospinal fluid surrounding it. The globe of the eye flattens at the back where the optic nerve enters, distorting the focal length. Folds develop in the tissue surrounding the optic nerve. The choroid, a layer of blood vessels feeding the retina, thickens in ways that alter visual function. Cotton wool spots, small areas of damaged retinal tissue, appear in some astronauts. These structural changes alter the eye's ability to focus, typically producing farsightedness that makes it difficult to read instruments or perform close work essential for mission operations. Scientists believe the syndrome results from increased pressure within the skull, created by the headward fluid shift that occurs in microgravity. On Earth, gravity pulls cerebrospinal fluid downward when you stand or sit upright. This creates a daily pressure cycle where intracranial pressure rises when lying down and falls when upright. In microgravity, this fluid redistributes permanently to a position between the lying down and standing configurations. The result is chronically elevated intracranial pressure that the brain and eyes were never evolved to tolerate continuously. The optic nerve passes through a channel connecting the brain and eye. The optic nerve sheath, which is filled with cerebrospinal fluid. Increased pressure in this sheath appears to damage the nerve where it enters the eye. The elevated pressure may also directly distort the eyeball, flattening its back surface and changing its optical properties. These changes progress throughout missions with no plateau in sight. The longer astronauts stay in space, the more their vision deteriorates. Exercise and lower body negative pressure devices provide some protection but cannot eliminate the problem. Lower body negative pressure applies suction to the legs, pulling fluid back toward the feet and temporarily reducing intracranial pressure. Astronauts use these devices for periods each day. but the effects are temporary. As soon as the session ends, fluid redistributes and pressure rises again. The fundamental cause is fluid redistribution driven by the absence of gravity, and this redistribution cannot be completely prevented, while astronauts live and work in microgravity environments. Long-duration astronauts report headaches, visual disturbances, and difficulty concentrating that may relate to elevated intracranial pressure. These symptoms vary considerably between individuals, with some astronauts experiencing severe problems while others notice only mild effects. The variation likely reflects differences in anatomy and physiology that affect how individuals respond to chronic pressure elevation. But the underlying mechanism affects everyone exposed to microgravity. The question is not whether pressure rises, but how much damage that elevated pressure causes before the mission ends. The full consequences of spending years with chronically elevated pressure on brain tissue remain unknown because no one has yet attempted missions long enough to find out. Studies of patients with idiopathic intracranial hypertension, a condition that produces similar pressure elevation on Earth, show progressive visual loss over time without treatment. The trend visible in 6-month to 1-year missions suggests that longer exposures would produce more severe and more permanent damage. This represents another dimension of the biological survivability ceiling, a limit on how long human eyes and brains can tolerate conditions they never evolved to withstand. The vestibular system, which provides balance and spatial orientation, faces its own set of challenges in microgravity that create problems both during missions and after return. This system evolved to function in gravity. It uses the weight of tiny calcium carbonate crystals called otoliths, pressing against sensory hair cells to detect which way is down. When you tilt your head, gravity pulls these crystals in a new direction, bending the hair cells and signaling the change in orientation to your brain. This system provides the unconscious awareness of body position that allows you to balance, walk, and orient yourself in space. In microgravity, these crystals provide no directional information because no gravitational force acts on them. They float neutrally, regardless of head position. The vestibular system receives inputs that conflict with visual information and proprioceptive signals from muscles and joints. Your eyes might tell you which way is up relative to the spacecraft interior, but your vestibular system provides no confirmation. This sensory mismatch confuses the brain's spatial processing systems in ways that take time to resolve. This sensory conflict produces space motion sickness in approximately 2/3 of astronauts during their first days in orbit. Symptoms include nausea, vomiting, disorientation, and difficulty concentrating. Most astronauts adapt within a few days as their brains learn to reweight sensory inputs, relying more heavily on vision and proprioception while discounting the confusing vestibular signals. This neural plasticity allows astronauts to function effectively in microgravity after the initial adaptation period. But this adaptation creates problems for the return to gravity. Astronauts who have adapted to microgravity experience disorientation and balance difficulties when gravitational loading returns. The brain has learned to ignore vestibular input that suddenly becomes meaningful again. It must readapt to using vestibular signals it had trained itself to discount. This readaptation process can take days or weeks, during which astronauts experience impaired balance that makes walking difficult and increases fall risk. Studies of astronaut vestibular function show measurable changes in otolith organ sensitivity following spaceflight. The otoliths themselves may undergo physical changes in microgravity, altering their mass or distribution in ways that affect their function when gravity returns. These changes can persist for weeks after landing and may contribute to the increased fall risk observed among returned astronauts. Falls are particularly dangerous for astronauts because their weakened bones fracture more easily than pre-flight, creating a compound vulnerability where damaged balance systems threaten damaged skeletal structures. This brings us back to the biological reality underlying the survivability ceiling. The human body cannot exist in microgravity indefinitely without suffering cumulative damage that exceeds its repair capacity. Exercise and pharmaceuticals can slow the deterioration. They cannot stop it. The body continues losing bone mass despite bisphosphonates. Muscles continue atrophying despite 2 hours of daily exercise. Hearts continue remodeling despite cardiovascular workouts. Eyes continue changing despite lower body negative pressure sessions. At a certain point, survival becomes deterioration, and the distinction between being alive and being functional collapses. The body was built for Earth. This is not a poetic statement, but a biological fact encoded in every tissue and organ system. 4 billion years of evolution, optimized human physiology for a 1G environment with constant gravitational loading, predictable fluid distribution, and mechanical stimuli that maintain structural integrity. Every system in the human body assumes gravity as a background condition. Remove that condition, and the body begins remodeling itself for an environment it was never designed to inhabit. The longest continuous spaceflight on record lasted 437 days, completed by Russian cosmonaut Valery Polyakov aboard the Mir space station in 1995. Polyakov returned to Earth and walked away from his landing vehicle. A remarkable achievement that demonstrated the outer limits of what rigorous countermeasures could accomplish. But extensive rehabilitation was required before he regained normal function, and his physiology showed significant changes despite the most rigorous countermeasure protocols available at the time. NASA astronaut Scott Kelly completed 340 days aboard the International Space Station in 2015 and 2016. As part of a twin study comparing his health to his identical twin brother Mark, who remained on Earth. The results documented physiological changes across multiple systems, including bone, muscle, cardiovascular, visual, and even genetic markers. Many changes reversed after return to Earth, but some persisted, and the study provided the most detailed evidence to date of what long-duration spaceflight does to human biology. A Mars mission would require astronauts to spend roughly 6 months traveling to Mars in microgravity, up to 18 months on the Martian surface, and 6 months returning in microgravity again. The transit phases would occur in zero gravity, adding to the physiological burden despite whatever countermeasures spacecraft could provide. Mars' surface gravity is only 38% of Earth's, insufficient to maintain Earth-adapted physiology even during the surface stay. Astronauts on Mars would continue experiencing bone loss, muscle atrophy, and cardiovascular deconditioning, just at slower rates than in microgravity. The total mission duration would exceed current long-duration spaceflight experience by a factor of 2 to 3. The cumulative effects on bone, muscle, cardiovascular, visual, and vestibular systems would be proportionally greater. Astronauts arriving at Mars after 6 months in microgravity would need to perform demanding physical tasks, including surface operations in spacesuits, while dealing with physiological impairment from the transit. The return journey would add another 6 months of microgravity exposure to systems already compromised by the outbound journey and inadequately recovered during the surface stay. Recovery after such a mission might never be complete. The skeleton that an astronaut brings back from Mars might remain permanently weakened compared to pre-flight condition, with lost trabecular architecture that cannot be rebuilt. Vision changes from 2 years of elevated intracranial pressure might not fully resolve. Cardiovascular deconditioning might contribute to premature aging and elevated disease risk for the remainder of the astronaut's life. The price of a Mars mission would be paid in biological currency that astronauts cannot earn back, a permanent reduction in health and function that no amount of post-mission rehabilitation could restore. Yet the body's response to microgravity represents only part of the survivability ceiling. Even if artificial gravity could somehow provide perfect gravitational loading throughout a mission, eliminating the bone loss and muscle atrophy and cardiovascular changes and vision problems, other factors would still impose strict limits on human survival in space. The mind faces its own assault, and the damage it accumulates may be just as limiting as what happens to flesh and bone. The human brain requires specific environmental inputs to function properly. It needs regular sleep cycles synchronized to light and dark. It needs social interaction to maintain psychological equilibrium. It needs sensory variety to prevent perceptual dysfunction. It needs the possibility of escape and some measure of control over its environment to manage stress responses that evolved for entirely different circumstances. Space provides none of these things. The resulting psychological and neurological deterioration adds another pillar to the biological survivability ceiling that no amount of mission planning, crew selection, or psychological training can fully address. Your brain is not a computer that can run indefinitely given adequate power. It is a biological organ with specific operating requirements shaped by hundreds of millions of years of evolution on a planet with predictable day-night cycles, rich social environments, and the constant possibility of movement away from threatening situations. Violate these requirements and the brain begins malfunctioning in ways that compound every other challenge of long-duration spaceflight. Circadian rhythms represent one of the oldest biological systems on Earth, predating complex life by billions of years. Single-celled organisms developed internal clocks synchronized to the planet's rotation before multicellular life evolved. Every cell in your body contains molecular machinery that tracks the passage of 24 hours through cycles of gene expression, protein synthesis, and metabolic activity. These cellular clocks coordinate with each other through hormonal signals, creating a body-wide rhythm that regulates sleep and wakefulness. Hormone release, body temperature, cognitive performance, immune function, and dozens of other physiological processes. The master clock resides in the suprachiasmatic nucleus, a tiny region of the hypothalamus containing approximately 20,000 neurons that synchronize the body's cellular clocks to environmental light cues. Light entering the eye triggers signals that reset this master clock daily, keeping internal time aligned with external reality. This synchronization system evolved under conditions where light meant day and darkness meant night, a reliable pattern that held true for the entire history of life on Earth. Astronauts on the International Space Station witness approximately 16 sunrises and sunsets every 24 hours as the station orbits Earth once every 90 minutes. This rapid cycling provides no useful signal for circadian synchronization. The body's clock-setting machinery cannot track light cycles that repeat 16 times faster than the rhythm it evolved to follow. Instead of synchronizing, the circadian system becomes confused, receiving contradictory signals that prevent stable entrainment to any consistent pattern. Space station lighting systems attempt to simulate day-night cycles using LED panels that shift color temperature throughout the day, providing blue-enriched light during work periods and warmer light before sleep. These systems represent significant improvements over earlier spacecraft lighting, but they cannot overcome the fundamental problem of an environment where sunrise occurs every 45 minutes, and where operational demands frequently override lighting schedules. Emergency situations, critical experiments, and communication windows with Earth do not pause for sleep schedules. The confined environment compounds lighting challenges. On Earth, you experience bright outdoor light during the day and relative darkness at night, with intensity differences spanning several orders of magnitude. Spacecraft interiors maintain relatively constant illumination levels that never approach the brightness of outdoor sunlight or the darkness of a properly darkened bedroom. The dynamic range of light exposure that helps maintain robust circadian rhythms simply does not exist inside a metal tube orbiting Earth. Astronauts report chronic sleep deprivation, averaging less than 6 hours of sleep per night compared to the 7 to 8 hours recommended for optimal function. Sleep studies conducted aboard the space station using wrist-worn monitors and polysomnography to confirm these reports. Astronauts take longer to fall asleep, wake more frequently during sleep periods, and spend less time in the deep sleep stages critical for physical restoration and memory consolidation. Even astronauts who report feeling rested show objective sleep deficits when monitored instrumentally. The consequences of chronic sleep deprivation are well documented through decades of research on Earth. Cognitive performance degrades measurably after even one night of inadequate sleep. Reaction time slows by percentages that matter when operating complex machinery or responding to emergencies. Working memory capacity decreases, making it harder to hold multiple pieces of information in mind simultaneously. Memory consolidation fails, meaning that learning and skill acquisition suffer. Emotional regulation deteriorates, making minor irritations feel like major provocations and reducing the patience needed for smooth interpersonal interactions. After multiple nights of poor sleep, performance impairment can equal that of legal alcohol intoxication. Studies comparing sleep-deprived subjects to subjects given measured doses of alcohol show equivalent impairment on tests of reaction time, attention, and judgment. Someone who has slept 4 hours per night for a week performs comparably to someone with a blood alcohol level of 0.08%, the legal limit for driving in most jurisdictions. Yet, we would never permit a drunk astronaut to operate a spacecraft or conduct a spacewalk. Long-duration astronauts operate in a state of chronic sleep debt that would disqualify them from most safety-sensitive positions on Earth. They perform complex tasks requiring precision and judgment while experiencing cognitive impairment that ground-based safety protocols would never permit. Air traffic controllers face mandatory rest requirements. Pilots cannot fly beyond duty time limits. Surgeons are restricted from operating after excessive hours. Astronauts follow schedules that would violate regulations in all these professions while facing consequences of error far more severe than any terrestrial occupation. The demands of spaceflight require continuous vigilance. Equipment failures can occur at any moment. Experiments require precise timing and careful execution. Communication windows with Earth come at scheduled times regardless of crew fatigue. Emergency scenarios demand immediate response, with no opportunity to wake up properly first. The space environment makes restorative sleep extremely difficult to achieve while simultaneously demanding peak cognitive performance around the clock. Mission Control provides scheduling assistance and monitoring, but cannot force sleep quality to improve. Controllers can adjust schedules to provide adequate time for sleep, but they cannot make astronauts actually sleep during that time. They cannot prevent the noise of equipment fans, the discomfort of sleeping in an unnatural position, or the psychological stress that keeps minds racing when bodies need rest. Sleep is a biological process that responds to environmental and psychological conditions. In space, those conditions work against restful sleep at every turn. Sleeping in microgravity presents unique challenges that no amount of schedule optimization can resolve. Without gravity, the distinction between lying down and standing up disappears. The body position that signals sleep to Earth-adapted brains has no meaning in space. You cannot feel the pressure of a mattress against your back or the weight of blankets pressing down. Astronauts sleep in bags attached to walls, floating in positions that provide no proprioceptive feedback indicating rest. Many astronauts report that sleep never feels fully restorative, regardless of how many hours they spend in their sleeping bags. They wake feeling unrested, even after sleeping their full allotted time. The subjective quality of sleep suffers, along with the objective duration. Some researchers speculate that the absence of gravitational pressure affects blood flow to the brain during sleep in ways that impair the restorative processes sleep normally provides. Whatever the mechanism, the result is clear. Space does not allow the quality of sleep that human biology requires. Beyond circadian disruption, isolation and confinement create psychological pressures that compound over time in ways that Earth-based experience poorly predicts. Human beings evolved as social creatures living in groups of dozens to hundreds of individuals. Our ancestors survived through cooperation, sharing information about food sources and dangers, coordinating hunting and gathering activities, caring for young collectively, and maintaining social bonds that provided security against a threatening world. The psychological need for social interaction, variety, and control over one's environment is not a preference that modern humans can simply override through willpower. It is a requirement for mental health encoded in neural architecture that evolved under conditions radically different from spacecraft interiors. Space missions confine small groups of people in volumes comparable to a modest apartment. The International Space Station provides approximately 900 cubic meters of habitable volume for crew sizes typically ranging from 3 to 6 people. This sounds spacious until you consider that the volume is distributed across multiple modules connected by narrow hatches, that much of the space is occupied by equipment and supplies, and that astronauts cannot simply step outside when they need a break from their crewmates. A Mars transit vehicle might provide significantly less space per person, perhaps 100 cubic meters each, for journeys lasting months without possibility of resupply or crew rotation. These confined environments offer no privacy worthy of the name. Astronauts sleep in quarters separated by thin walls or curtains. They use toilet facilities within earshot of crewmates. They eat every meal together, work in close proximity throughout the day, and share recreational time in the few hours available for relaxation. The social environment is more constrained than a prison, where inmates at least have cells they can retreat to and yards they can walk in. Astronauts have no escape from their crewmates and no ability to leave when interpersonal tensions arise. Psychological research from analog environments provides disturbing predictions for long-duration space missions. Antarctic winter-over crews spend months isolated in small groups with no possibility of evacuation during the polar winter. Submarine crews remain submerged for deployments lasting months, with minimal contact with the outside world. Isolation study participants voluntarily confine themselves in closed environments to simulate space mission conditions. All these populations show elevated rates of depression, anxiety, and interpersonal conflict during extended confinement. These effects intensify over time and can produce acute psychological crises requiring intervention. The third quarter phenomenon describes a pattern observed across many isolation studies that carries ominous implications for Mars missions. Psychological difficulties peak during the third quarter of a mission, regardless of total duration. A 60-day isolation study shows peak distress around day 45. A 6-month Antarctic winter shows peak problems around month 4. This pattern suggests that the psychological system responds to perceived mission progress rather than absolute time elapsed. The brain somehow tracks how far through an ordeal it has come and how far remains to go, and something about the 3/4 point triggers maximum psychological strain. For a 3-year Mars mission, the third quarter would coincide with the surface stay on Mars, when operational demands are highest and the consequences of psychological breakdown would be most severe. Astronauts experiencing peak depression and interpersonal conflict would need to conduct complex surface operations, maintain critical equipment, and support each other through challenges that cannot be postponed. The timing could not be worse if deliberately designed to maximize mission risk. Communication delays add another dimension to psychological stress that no previous human expedition has faced. Near Earth. Astronauts can speak with family and mission control in near real time. The lag is imperceptible, measured in fractions of a second. This continuous connection provides emotional support when homesickness strikes. It provides immediate technical assistance when equipment malfunctions. It provides the psychological comfort of knowing that someone is always listening, always available, always able to help if problems exceed local capability to solve. Mars missions would face communication delays of 4 to 24 minutes each way, depending on the orbital positions of Earth and Mars. When the planets are closest, signals take about 4 minutes to travel between them. When they are on opposite sides of the Sun, the delay extends to 24 minutes. A 20-minute one-way delay means 40-minute round-trip conversations, where each exchange requires waiting longer than most people wait in line at the grocery store. Real-time conversation becomes impossible. Astronauts would need to send messages and wait substantial periods for any response, transforming dialogue into an exchange of monologues separated by uncomfortable silences. This communication lag fundamentally changes the relationship between crew and ground support in ways that affect both practical operations and psychological well-being. Astronauts cannot call home when they need emotional support and receive immediate comfort. A message sent during a moment of distress will not receive a response for the better part of an hour, by which time the acute emotional need may have passed or intensified into something worse. They cannot ask mission control for help and receive guidance before a problem escalates. An equipment malfunction that occurs at the start of a work shift cannot receive Earth-based troubleshooting assistance until the end of that shift or later. The psychological buffer provided by continuous Earth connection disappears entirely, leaving crew members genuinely alone in ways no previous astronauts have experienced. Low Earth orbit astronauts know that help is always available in real time, that family voices are only a phone call away, that mission control monitors their status continuously and can intervene immediately if problems develop. Mars astronauts would know that they are on their own for minutes or hours regardless of what happens, that emotional support comes on delay, if it comes at all, that technical problems must be handled locally or not at all until enough time passes for light-speed communication to catch up with events. Psychological research suggests that perceived control over one's environment significantly affects stress responses in ways that matter profoundly for long-duration spaceflight. People tolerate difficult conditions better when they believe they can escape or modify their situation. A worker enduring a stressful job derives psychological protection from knowing they could quit. A resident enduring a noisy neighborhood draws comfort from the theoretical possibility of moving. Even the perception of control, whether or not it is actually exercised, provides measurable protection against stress-related health consequences. Astronauts on Mars cannot leave. They cannot call for rescue, because no rescue capability exists. They cannot receive emergency resupply because the next launch window might be months away, and the transit time adds months more. The knowledge that problems must be solved with whatever resources are available, with no possibility of external assistance arriving on any useful timescale, creates a psychological burden qualitatively different from any previous human expedition. Antarctic researchers can be evacuated in emergencies. Submarine crews can surface if critical problems develop. Mars astronauts have no such options, and they will know this every moment of their multi-year mission. Cognitive function in space shows measurable decline beyond what sleep deprivation alone would explain, suggesting that additional mechanisms impair brain function in the space environment. Studies using standardized cognitive tests administered to astronauts before, during, and after missions show decreased performance on tasks involving spatial reasoning, memory, and executive function. These deficits appear in astronauts who report adequate sleep and show no obvious signs of psychological distress. Something about the space environment impairs cognition through pathways not fully explained by other known factors. Carbon dioxide levels in spacecraft typically run 5 to 10 times higher than Earth's surface concentrations due to the challenges of air revitalization in closed environments. Earth's atmosphere contains approximately 400 parts per million of carbon dioxide. Spacecraft atmospheres commonly contain 2,000 to 5,000 parts per million, sometimes higher during periods of intense crew activity or when scrubbing equipment operates at reduced efficiency. Research on Earth demonstrates that elevated carbon dioxide impairs cognitive function even at levels well below those common on the space station. Studies exposing healthy subjects to different carbon dioxide concentrations show measurable cognitive decrements at levels above 1,000 parts per million. Decision-making quality declines. Strategic thinking suffers. The ability to process complex information and reach sound conclusions degrades in proportion to carbon dioxide concentration. Spacecraft crews live and work in atmospheres that would trigger ventilation system alarms in most Earth buildings. Atmospheres that research suggests impair the very cognitive functions most critical for mission success. The immune system deteriorates in space in ways that increase vulnerability to infection, while simultaneously reactivating latent viruses that healthy immune systems normally keep suppressed. Studies analyzing blood samples from astronauts show decreased function of natural killer cells, the immune system's first-line defense against infected cells and cancer. T-cell function changes in ways that reduce the ability to mount effective responses against novel pathogens. Cytokine profiles shift toward patterns associated with chronic inflammation, rather than effective immune surveillance. Simultaneously, viruses like herpes simplex and varicella zoster that remain dormant in most healthy adults begin reactivating and shedding during spaceflight. These viruses establish lifelong latent infections in nerve cells, normally kept suppressed by continuous immune surveillance. When immune function declines, the viruses emerge from dormancy and begin replicating. Astronauts show elevated viral shedding in saliva and other body fluids, potentially increasing infection risk for crewmates. Even though the shedding astronaut may show no symptoms, this immune dysregulation appears to result from multiple factors working together in ways that cannot be fully separated. Stress hormones like cortisol suppress immune function as part of the body's normal response to perceived threats. Chronic stress keeps cortisol elevated, maintaining immune suppression long beyond its usefulness. Disrupted sleep impairs the immune processes that normally occur during rest. Radiation exposure damages immune cells directly. Changes in the microbiome, the community of bacteria and other microorganisms inhabiting the gut, alter the immune signaling that normally maintains proper function. Astronauts carry microbial communities that shift in composition during spaceflight, potentially affecting immune function and overall health in ways scientists are only beginning to understand. The gut microbiome helps train the immune system, produces vitamins and other essential compounds, and influences brain function through the gut-brain axis. Changes in this microbial community could have cascading effects throughout multiple body systems that current research has not yet fully characterized. The convergence of all these stressors creates conditions where damage in one system accelerates damage in others, producing cascade failures that escalate faster than any individual mechanism would suggest. Poor sleep impairs immune function. Immune dysfunction increases infection risk, which increases stress. Stress disrupts sleep further, creating a feedback loop that amplifies both problems. Cognitive impairment from sleep deprivation and elevated carbon dioxide reduces ability to maintain the rigorous exercise protocols that protect against musculoskeletal deterioration discussed in Part 2. Psychological strain from isolation and communication delays reduces motivation for self-care behaviors that might otherwise provide some protection against physical decline. Each system failure creates conditions that accelerate failures in connected systems. The body and mind do not exist as independent components that can be analyzed separately and summed to predict total risk. They interact continuously, with problems in one domain creating problems in others through mechanisms that multiply rather than simply add. This cascade effect means that the risks of long-duration spaceflight cannot be calculated by summing individual risk factors and assuming independence. The interactions between systems create multiplicative rather than additive effects. Total mission risk exceeds the sum of individual component risks because the components interact in ways that amplify each other beyond what isolated analysis would predict. Consider how the factors discussed across all three parts of this documentary might interact in practice. Radiation exposure from Part 1 damages DNA and increases cancer risk. It also damages neurons and may impair cognitive function directly. Sleep deprivation from circadian disruption impairs DNA repair mechanisms, potentially amplifying the radiation damage that would otherwise be partially corrected. Immune suppression reduces the body's ability to eliminate cells with radiation-damaged DNA before they become cancerous. Stress hormones from psychological factors further suppress immune function while also accelerating bone loss through mechanisms involving cortisol's effects on osteoblast activity. The cascade continues. Weakened bones from microgravity exposure create chronic pain that disrupts sleep further. Impaired sleep reduces cognitive function needed to maintain exercise, protocols that slow bone loss. Psychological strain from isolation reduces motivation to exercise, even when cognitive function would permit it. Cardiovascular deconditioning reduces exercise capacity, making even motivated astronauts unable to maintain protective protocols. Vision changes from elevated intracranial pressure make it harder to read instruments and perform tasks, increasing stress and reducing performance on cognitive tests. Each thread connects to every other thread in a web of mutual amplification. Pulling any single thread tightens the entire web. The biological survivability ceiling emerges not from any single factor reaching a critical threshold, but from the integrated stress across all systems exceeding what the organism can sustain. Data from the International Space Station provides the best available evidence for these effects. But ISS missions have limitations that make them imperfect predictors of Mars mission outcomes. The station remains in low Earth orbit where communication delays are negligible, where emergency evacuation is possible within hours, using Soyuz or Dragon spacecraft, and where resupply can occur regularly to replace failed equipment and refresh supplies. Astronauts on the station know that help is only hours away if serious problems develop. This knowledge provides psychological protection that Mars astronauts will not have. A Mars mission would remove all these safety buffers while extending mission duration by a factor of 3 or more compared to current ISS expeditions. The psychological knowledge that no rescue is possible, that problems must be solved with available resources alone, that years will pass before return to Earth becomes possible, adds stress that no Earth-based analogue can fully simulate. Antarctic stations can evacuate in emergencies, submarine crews can surface, isolation study participants can abort. Mars crews will have none of these options, and they will carry that knowledge every day for years. Mental limits are biological limits. This statement deserves emphasis, because popular culture often treats psychological resilience as something that can be willed into existence through sufficient determination. The brain is an organ, subject to the same biological constraints as every other tissue in the body. It requires specific inputs to function properly, just as the heart requires oxygen, and the bones require calcium. Psychological stress produces measurable physiological changes: elevated cortisol, altered immune function, changed brain structure visible on imaging studies, modified gene expression patterns that can persist long after stresses end. These are not merely subjective experiences that astronauts could choose to ignore with sufficient willpower or training. They are biological responses to environmental conditions that violate the brain's evolved operating parameters. No amount of determination can make circadian rhythms synchronize to 90-minute orbital cycles. No strength of will can prevent stress hormones from rising during years of isolation and confinement. No psychological technique can give the brain the varied sensory input it requires to maintain normal function when the environment provides only the monotonous interior of a spacecraft. Long-duration isolation studies provide upper bounds on how long people can maintain psychological function under confined conditions, and those bounds carry implications for the biological survivability ceiling. Even with optimal selection of participants choosing the most psychologically resilient individuals available, careful mission design, providing the best possible conditions, and extensive support from outside, including real-time communication and abort options, isolation studies lasting more than a year show significant rates of psychological disturbance among participants. Depression develops, anxiety escalates, interpersonal conflict intensifies, cognitive function declines in ways that affect task performance. These studies occurred on Earth. With full gravity, normal atmospheric composition, immediate communication, and the knowledge that participants could abort if necessary. Space missions remove all these protective factors while adding radiation exposure, chronic sleep disruption, cardiovascular and musculoskeletal deterioration, immune compromise, elevated carbon dioxide, and the knowledge that abort is not an option. The psychological burden of spaceflight exceeds what Earth-based analogues can model because spaceflight simultaneously impairs the biological systems that would normally provide resilience against psychological stress. No amount of psychological screening can identify astronauts immune to these effects. Selection processes can identify candidates with superior baseline psychological function, filtering out individuals with histories of mental illness or poor stress tolerance. But no selection process can eliminate biological vulnerability to circadian disruption, sensory monotony, social isolation, or loss of control. These vulnerabilities are features of human neurology, not flaws in particular individuals. They exist because the brain evolved under conditions where they served adaptive purposes, conditions radically different from spacecraft environments. Training provides coping strategies but cannot fundamentally alter the brain's response to conditions it was never designed to endure. Astronauts trained for long-duration missions are among the most psychologically resilient people on Earth. They have been screened repeatedly for psychological fitness. They have received extensive training in stress management, interpersonal communication, and conflict resolution. They understand intellectually what they will face and have prepared as thoroughly as human knowledge permits. They still experience mood disturbances, cognitive impairment, and interpersonal difficulties during spaceflight. Training helps them manage these difficulties more effectively than untrained individuals would, but cannot prevent the difficulties from occurring in the first place. Pharmaceutical interventions offer limited assistance that carries its own costs. Sleep medications can help with acute insomnia, but create their own problems when used chronically, including dependence, rebound insomnia upon discontinuation, and next-day cognitive impairment that might be worse than the sleep deprivation they treat. Antidepressants and anxiolytics can moderate mood symptoms but affect cognitive function in ways that might impair mission performance, and their effects on brain chemistry during long-duration spaceflight have not been studied. There is no pill that makes isolation comfortable or gives the brain the varied sensory input it requires to maintain normal function. The implications for the biological survivability ceiling are clear and cannot be escaped through better technology or more rigorous selection and training. Human psychology places constraints on mission duration that interact with and compound the physical constraints already discussed. A mission that astronauts survive physically might still fail psychologically. The breaking point for the mind might arrive before the breaking point for the body, or the two might arrive together as cascading failures spread between systems that were never designed to operate under such sustained assault. Current evidence suggests that missions lasting 3 or more years would push psychological systems past their sustainable operating range for most people. Some individuals might fare better than average, reaching the mission's end with psychological function sufficient for continued survival and eventual recovery. Others would experience acute psychological crises requiring mission modification or abort, if abort were possible, which for Mars missions it would not be. The variation between individuals adds uncertainty to predictions, but does not eliminate the underlying biological ceiling. It merely makes the precise location of that ceiling difficult to predict for any particular crew. This brings us back to the fundamental biological reality that defines the survivability ceiling. The human brain evolved to function within specific environmental parameters. Violate those parameters for long enough, and the brain begins failing in ways that cascade through every other system. No amount of engineering changes the human brain's response to circadian disruption. No mission planning eliminates the psychological burden of years-long isolation without possibility of escape. At a certain point, survival becomes deterioration, and the mind reaches limits as absolute as any faced by flesh and bone. Every biological system discussed in this documentary converges toward a single conclusion. There exists a hard upper limit on how long human beings can survive in space environments. This limit is not set by rocket technology, life support engineering, or mission planning. It is not constrained by budget allocations, political will, or the courage of those willing to volunteer. It is set by the fundamental design parameters of human biology, parameters encoded in DNA over billions of years of earthbound evolution, parameters that cannot be changed by any technology humanity currently possesses or can reasonably project into the foreseeable future. The survivability ceiling emerges from the intersection of multiple damage mechanisms, each contributing to cumulative harm that eventually exceeds the body's repair capacity. This is not a theoretical construct or a pessimistic assumption. It is the mathematical consequence of biological systems operating outside their evolved parameters. Every hour in space adds damage. every day compounds it. Every month pushes closer to thresholds, beyond which recovery becomes impossible and function becomes unsustainable. Radiation damage accumulates in DNA with every particle that passes through tissue. Bone and muscle tissue deteriorate despite the most rigorous countermeasure protocols available. Cardiovascular systems decondition as hearts remodel for an environment that no longer requires their full Earth-adapted capacity. Vision degrades as elevated intracranial pressure reshapes the optic nerve and the globe of the eye. Vestibular function becomes unreliable as balance organs adapted for gravity receive meaningless signals in its absence. Sleep disruption impairs cognition and immune function through mechanisms that no scheduling adjustment can fully address. Psychological stress compounds all other effects through hormonal pathways that accelerate physical deterioration while simultaneously reducing the capacity to cope with it. None of these mechanisms operates independently. They interact in ways that accelerate total deterioration beyond what any single factor would produce alone. The human body functions as an integrated system, where every component depends on every other component. Damage one system, and you damage them all. Impair one function, and you impair the capacity to maintain other functions. The cascade effects documented throughout this investigation represent not isolated observations, but fundamental properties of biological organization. As documented in Part 3, these damage mechanisms do not operate independently. They interact through cascade effects where failure in one system accelerates failure in others. Weakened bones reduce exercise capacity, which accelerates further bone loss. Sleep deprivation impairs immunity, which increases infection risk, which elevates stress, which disrupts sleep further. Each system pulls the others down faster than any would fall alone. This is not speculation, but documented reality. Observed in astronauts returning from missions measured in months, extrapolated with increasing uncertainty toward missions measured in years. Scientists modeling these interactions have attempted to project cumulative mission risk across multi-year time horizons using data from the International Space Station, analog environments on Earth, animal studies, and theoretical frameworks from radiation biology, physiology, and psychology. The results consistently show nonlinear risk escalation that should concern anyone planning long-duration missions. Risk does not simply double when mission duration doubles. It increases by larger factors because damage accumulation creates feedback loops that accelerate deterioration over time. A 2-year mission is not twice as risky as a 1-year mission. It may be 3 or 4 times as risky, because the second year of damage compounds on a biological foundation already weakened by the first year. A 3-year mission compounds further still, with the third year attacking systems that have already exhausted much of their reserve capacity during the preceding 2 years. The mathematics of compound damage resembles the mathematics of compound interest, but in reverse. Where compound interest grows wealth exponentially over time, compound biological damage grows impairment exponentially. Small rates of deterioration that seem manageable over months become devastating over years. The bone loss rates documented in Part 2 sound minor on a monthly basis until you calculate their cumulative effect across a 3-year mission, leaving an astronaut with a skeleton dramatically weaker than at departure, even before accounting for the accelerating factors that make later losses worse than earlier ones. The difference between surviving and thriving becomes critical when calculating the survivability ceiling. An astronaut might survive a 3-year mission in the technical sense of remaining alive at mission end. Hearts would still beat, lungs would still breathe, brain activity would continue. By the minimal definition of survival as the absence of death, such an astronaut would have survived. But survival with permanently impaired vision that prevents reading or driving is not the same as survival with functional eyes. Survival with a skeleton so weakened that normal activities risk fracture is not the same as survival with bones capable of supporting an active life. Survival with cognitive deficits that impair memory and judgment is not the same as survival with a fully functional mind. Survival with chronic health problems, requiring ongoing medical management, is not the same as survival with robust health. The survivability ceiling must account not just for mission completion, but for quality of post-mission life. An astronaut who returns alive but permanently disabled has survived the mission in one sense while failing to survive in another. The relevant question is not whether astronauts can be kept breathing for the duration of a multi-year mission. The relevant question is whether they can return in condition to live meaningful lives afterward. Conservative estimates based on current data suggest that the probability of serious, permanent health consequences rises steeply for missions exceeding 2 years. Risk increases slowly at first, then accelerates as cumulative damage approaches thresholds where recovery becomes incomplete. Above 18 months, permanent changes become increasingly likely. Above 24 months, permanent changes become the expected outcome rather than the exception. Beyond 3 years, most astronauts would be expected to return with some form of lasting impairment, affecting quality of life and life expectancy. The specific impairments would vary between individuals based on genetic factors, countermeasure compliance, mission conditions, and simple chance. Some might suffer primarily skeletal damage. Others might experience vision loss as their dominant long-term problem. Still others might face cardiovascular disease, cognitive decline, or elevated cancer risk as their primary legacy of spaceflight. But the expectation of some significant permanent damage becomes near universal as mission duration extends beyond the 3-year threshold. Beyond 5 years, survival itself becomes uncertain. The accumulation of damage across all systems would push even the most resilient individuals toward failure points where critical functions can no longer be maintained. Those who survived would face dramatically shortened remaining lifespans and compromised physical and mental function that might make independent living impossible. The astronaut who departed in peak physical condition would return as a medical patient, requiring extensive and possibly lifelong care. These estimates carry substantial uncertainty because no human has yet attempted missions of these durations. The longest continuous spaceflight lasted 14 months. The cumulative experience of all astronauts who have ever flown totals less than 200 person-years in space, most of it in low Earth orbit, where conditions are significantly less hostile than deep space. Projections beyond current experience rely on extrapolating trends observed in missions lasting a year or less. Combined with biological modeling of damage mechanisms based on theory and animal studies, the extrapolations could underestimate or overestimate actual long-duration risks. Perhaps the human body adapts to space conditions in ways that current short-duration data does not reveal. Perhaps damage rates decrease over time as systems reach new equilibria. Perhaps countermeasures not yet developed will prove more effective than current options. These possibilities might shift the survivability ceiling outward, allowing longer missions than current projections suggest. Alternatively, perhaps currently unknown failure modes emerge only on longer missions. Perhaps damage mechanisms interact in ways that short-duration missions do not reveal. Perhaps systems that appear stable after 1 year begin failing after 2. These possibilities might shift the survivability ceiling inward, making even shorter missions more dangerous than current projections suggest. But the direction of the trend is clear, and no plausible adjustment to current data eliminates the survivability ceiling. Optimistic assumptions might place it at 4 years rather than 3. Pessimistic assumptions might place it at 2 years rather than 3. No realistic assumption places it at 10 years or 20 or indefinite. The ceiling exists. The only uncertainty concerns its precise location. Some observers propose that future medical advances will eventually remove these constraints entirely. Perhaps genetic engineering could enhance DNA repair capacity, allowing human cells to survive radiation doses that currently cause cancer and cellular dysfunction. Perhaps pharmaceutical interventions could halt bone loss completely, preserving skeletal integrity regardless of gravitational loading. Perhaps neural implants could protect against cognitive decline. Perhaps artificial organs could replace those damaged by spaceflight with engineered substitutes immune to the degradation affecting biological tissue. Perhaps humans could be modified to survive conditions that current biology cannot tolerate. This perspective fundamentally misunderstands the nature of the biological constraints involved. Human biology is not a collection of independent components that can be upgraded individually like replacing parts in a machine. It is an integrated system, where changes in one area propagate throughout the organism in ways that cannot be fully predicted or controlled. The body maintains itself through millions of years of evolutionary refinement that produce systems exquisitely adapted to each other and to their environment. Modifying any single system affects every other system it interacts with. Enhancing DNA repair might reduce cancer risk while creating other problems. The repair mechanisms that fix damaged DNA also participate in other cellular processes. Accelerating repair might interfere with normal cell division, development, or differentiation. The same enzymes that recognize and repair radiation damage also play roles in immune function, tissue maintenance, and protection against autoimmune disease. Enhancing their activity in one context might impair their function in others. Modifying bone metabolism to prevent loss might interfere with calcium homeostasis in ways that cause different failures. Bones serve not just as structural support, but as reservoirs of calcium that the body draws upon to maintain blood chemistry within narrow tolerances. Preventing bone resorption might cause calcium levels to fall, triggering cardiovascular, neurological, and muscular problems potentially more acute than the skeletal weakening it prevents. The body's systems interconnect in ways that make isolated modifications dangerous. Replacing organs with artificial substitutes trades organic failure modes for mechanical ones that may be worse in spaceflight environments. Mechanical hearts require power supplies that can fail. Artificial kidneys require consumables that must be resupplied. Synthetic components lack the regenerative capacity that allows biological organs to heal minor damage without intervention. A biological heart that weakens in microgravity can be rehabilitated after return to Earth. A mechanical heart that fails in deep space cannot be replaced. More fundamentally, the modifications required to eliminate spaceflight biological constraints would create organisms that are no longer human in any meaningful sense. The changes would not be adjustments or improvements to human biology. They would be replacements of human biology with something different. Radiation resistance, sufficient for multi-decade deep space exposure, would require replacing human cellular machinery with fundamentally different systems. Human cells use DNA as their genetic material and proteins as their functional molecules. This biochemistry is inherently vulnerable to ionizing radiation. Creating radiation-resistant cells would require either shielding DNA with structures that would change cellular function, or replacing DNA with alternative genetic systems that have different properties. Either approach produces cells that are not human cells. Bones that do not require gravitational loading would need different structure and regulation than human bones. Human bones maintain themselves through mechanical sensing that triggers repair and remodeling in response to stress. Removing this requirement means removing the mechanical sensing, which means removing the adaptive capacity that allows bones to strengthen in response to increased loading. The result would be static structures unable to adapt to changing demands, fundamentally different from the living tissue that human bones comprise. A psychology that thrives in permanent isolation would need different neural architecture than human brains possess. Human brains evolved for social living. The circuits that process social information, maintain emotional bonds, and respond to isolation with distress are not optional features that can be removed without consequence. They are integral to brain organization, connected to systems governing motivation, reward, learning, and memory. Creating a mind comfortable with permanent isolation would require restructuring the brain in ways that would change personality, cognition, and emotional experience beyond recognition. These modifications might be theoretically possible in some distant future, where biotechnology achieves capabilities far beyond current understanding. But the resulting beings would not be humans adapted for space. They would be new organisms designed for space, as different from current humans as humans are different from the distant ancestors who first crawled onto land hundreds of millions of years ago. The continuity of identity between modified space dwellers and their human ancestors would be questionable at best. The survivability ceiling for humans would remain exactly where it stands today. And at that point, the question of human survival in space becomes moot, because the beings surviving would no longer be human. For actual human beings, biological humans with DNA inherited from ancestors who evolved on Earth, the biological survivability ceiling represents a permanent constraint on how far and how long we can venture into space. This constraint exists regardless of how sophisticated our spacecraft become, regardless of how much we learn about space medicine, regardless of how carefully we select and train astronauts. The constraint is written in the structure of human cells and cannot be erased by any technology that preserves those cells as human. The implications for Mars missions deserve direct examination because Mars represents the most ambitious crewed mission currently under serious discussion. A minimal Mars mission would require approximately 2.5 to 3 years total duration, including roughly 6 months transit in each direction and up to 18 months on the Martian surface. This duration approaches or exceeds the range where current evidence suggests serious permanent consequences become likely for most astronauts. The timeline breaks down as follows. 6 months of outbound transit would occur in microgravity, accumulating all the damage documented in Part 2. Astronauts would arrive at Mars with bones already weakened by roughly 6 to 12%, muscles atrophied despite exercise countermeasures, cardiovascular systems deconditioned, vision potentially already changing from elevated intracranial pressure, and immune systems dysregulated from the combination of radiation, stress, and confinement. Mars surface operations would begin with astronauts already compromised by the transit. Mars gravity at 38% of Earth normal would slow but not halt further deterioration. Studies suggest that partial gravity provides partial protection, but no one knows precisely how much. The bone loss rate at 0.38 g might be half what it is in microgravity, or it might be 3/4, or it might provide nearly full protection. No human has spent extended time in partial gravity environments, so projections rely on animal studies and theoretical models with substantial uncertainty. Even assuming optimistic scenarios where Mars gravity provides significant protection, the cumulative damage would continue. Radiation on the Martian surface is lower than in deep space because the planet itself blocks half the sky, but remains far higher than on Earth due to Mars's thin atmosphere and lack of global magnetic field. Psychological stress would continue, as astronauts remain isolated from Earth with communication delays preventing real-time conversation. The surface mission might slow the deterioration rate, but it would not reverse the damage accumulated during transit. The return transit would add another 6 months of microgravity exposure to systems already damaged by the outbound journey and inadequately recovered during the surface stay. Whatever bone mass astronauts regained on Mars would begin disappearing again. Whatever psychological equilibrium they achieved would face renewed assault from the confinement, monotony, and awareness that Earth remains months away. Astronauts returning from such a mission would likely require extensive rehabilitation lasting months or years. They might never fully recover their pre-mission health status. Some might experience permanent disabilities affecting mobility, vision, cognition, or other functions. A fraction might not survive the mission at all, succumbing to acute illness, accident, or systems failure while operating with impaired cognition and reduced physical capacity. The mission that departed with a healthy crew might return with a crew permanently diminished by the journey. These risks might be acceptable for missions of extraordinary scientific or strategic importance. Astronauts might volunteer knowing the costs, accepting permanent health damage as the price of making history. Society might decide that certain achievements justify sacrificing the health of willing participants, as it has decided for other dangerous endeavors throughout human history. Exploration has always carried costs, and those costs have sometimes included the lives and health of explorers who accepted them knowingly. But the risks cannot be wished away by believing that better technology will eliminate them before missions depart. The biological survivability ceiling exists now and will continue to exist for the foreseeable future. Planning Mars missions requires acknowledging this reality, rather than assuming future breakthroughs will solve problems that current biology cannot. The survivability ceiling does not prevent humans from going to Mars. It means that going to Mars will cost more than rocket fuel and mission planning. It will cost human bodies and minds. It will cost years of healthy life extracted from whoever makes the journey. Some portion of those costs cannot be recovered. The astronauts who walk on Mars will pay a permanent price in health and life expectancy that no post-mission rehabilitation will fully restore. This is the price of human spaceflight beyond the protective cocoon of Earth's environment, and it cannot be avoided through any technology we can currently imagine. The question for society is whether the achievements justify the costs, not whether the costs can be eliminated. Longer duration missions face proportionally worse prospects that multiply rather than merely add. A human voyage to the asteroid belt lasting 5 years would almost certainly return astronauts in condition requiring extensive medical care for the remainder of shortened lives. A voyage to Jupiter lasting 8 years would push beyond the survivability ceiling for most crew members, with uncertain prospects for any returning alive and functional. A voyage to Saturn or beyond lasting a decade or more would almost certainly kill its crew through accumulated biological damage. Even if all spacecraft systems functioned perfectly and no accidents occurred, interstellar missions lasting decades or centuries are beyond discussion for biological humans under any plausible technological scenario. The damage mechanisms operate continuously, regardless of distance traveled. An astronaut spending 30 years crossing to Alpha Centauri would accumulate 30 years of radiation damage, 30 years of microgravity effects, 30 years of psychological strain. No biological human could survive such exposure regardless of the spacecraft carrying them. The dreams of human space colonization require confronting this biological reality with clear eyes and honest assessment. Permanent human presence beyond Earth would require solving the radiation problem, the microgravity problem, and all the problems we have not yet discovered because no one has attempted missions long enough to reveal them. Each problem has potential solutions, but each solution adds complexity, cost, and failure modes to already challenging endeavors. Rotating space habitats might provide artificial gravity sufficient to maintain bone, muscle, and cardiovascular health. The engineering challenges are substantial but not obviously impossible. Such habitats would need to rotate at rates that provide at least partial gravity without causing motion sickness from the Coriolis effect. They would need to be large enough that the rotation rate remains comfortable. They would need structural integrity to withstand the stresses of continuous rotation for years or decades. Each requirement adds mass, complexity, and failure modes. Underground colonies might provide radiation shielding sufficient to reduce exposure to near-Earth levels. Burying habitats beneath meters of regolith would block most cosmic radiation, creating environments where long-term habitation becomes biologically feasible. But underground construction on other worlds presents enormous engineering challenges. The equipment required is massive, the energy requirements substantial, the timelines measured in years or decades before habitats become ready for occupation. Carefully designed social structures might provide psychological support sufficient to maintain mental health during extended missions. Larger crews reduce individual isolation. Varied activities combat monotony. Communication systems that minimize delay effects might help maintain connections with Earth. Virtual reality might provide simulated environments that relieve confinement stress. Each intervention helps, but none eliminates the fundamental challenge of human minds operating outside their evolved parameters. Nothing in the currently projected future of human technology eliminates the biological survivability ceiling. It can be pushed somewhat through better countermeasures that reduce damage rates. It can be approached more closely through accepting greater risk and acknowledging higher probabilities of permanent impairment. It can be worked around through infrastructure development that reduces mission durations or provides better environmental control. But it cannot be removed without ceasing to be human. This conclusion might seem pessimistic to those who dream of humanity spreading across the cosmos, establishing colonies on Mars and the moons of Jupiter, eventually reaching for the stars. It is not pessimism. It is realism about what human biology permits and what it forbids. Understanding limits allows working within them effectively, rather than denying them until they assert themselves through tragedy. The universe is vast beyond comprehension, containing wonders that humanity has only begun to discover. The cosmos extends billions of light years in every direction, harboring trillions of galaxies, each containing hundreds of billions of stars, many orbited by planets where conditions unknown to Earth might prevail. The scale of existence dwarfs human imagination and will never be fully explored by any species, regardless of how long it survives or how far it travels. But the beings doing the discovering will remain bound by the biology they carry with them. Human explorers will remain human, with all the capabilities and limitations that human biology implies. They will need to breathe, eat, sleep, and maintain the physiological parameters that keep human bodies functioning. They will accumulate damage from radiation and suffer from microgravity. They will experience psychological strain from isolation and confinement. They will age and eventually die, regardless of how far they travel or what they accomplish. There is profound significance in understanding our limits as well as our capabilities. Every human achievement exists within constraints that define what is possible and what is not. We cannot fly by flapping our arms, regardless of how much we wish to soar. We cannot breathe underwater without technological assistance, regardless of how much we wish to explore the depths. We cannot survive indefinitely without food and water, regardless of how inconvenient that requirement becomes. We cannot live forever regardless of how much we fear death. These are not failures of human potential, they are facts about what kind of beings we are. They define the human condition as much as our remarkable capabilities for learning, creating, and exploring. Acknowledging limits does not diminish human achievement. It contextualizes achievement within realistic frameworks that allow meaningful assessment of what we have accomplished and what we might yet accomplish. The biological survivability ceiling in space is another such fact. It tells us that human bodies are Earth-adapted organisms, exquisitely suited to the environment that shaped their evolution over billions of years, increasingly impaired as conditions diverge from that evolutionary baseline. No ancestor ever experienced microgravity, cosmic radiation, or years of isolation in confined spaces. The body responds to these conditions by deteriorating in ways that evolution never provided mechanisms to prevent. Understanding this limit matters because it shapes realistic planning for humanity's future in space. Missions must be designed with biological constraints as primary parameters, not afterthoughts to be addressed after propulsion and payload concerns are satisfied. Astronaut health must be treated as a limiting factor equivalent in importance to propulsion and life support. Post-mission care and rehabilitation must be planned from the start, rather than improvised after damage becomes apparent. The true costs of exploration must be acknowledged honestly, rather than minimized in pursuit of funding or public support. The astronauts who venture beyond Earth's protection deserve honesty about what their journeys will cost them. They deserve accurate information about the risks they accept, the damage they will accumulate, and the long-term consequences they will face. They deserve respect for their willingness to pay these costs in service of exploration, and they deserve medical care commensurate with the sacrifices they make. The public that funds and celebrates these missions deserves accurate information about human capability and limitation. Space agencies that downplay risks to secure funding do a disservice to both astronauts and taxpayers. Public support built on unrealistic expectations will collapse when reality asserts itself through mission failures or astronaut deaths. Sustainable space programs require honest communication about what is possible and what is not. The scientific community that studies space medicine deserves recognition that their findings constrain mission possibilities rather than simply supporting them. Researchers who document damage mechanisms and survivability limits perform essential work that must inform mission planning even when their conclusions are unwelcome. Shooting the messenger does not change the message. Human spaceflight is a genuine achievement worthy of celebration. Every astronaut who has orbited Earth has demonstrated human courage and capability in environments utterly unlike those for which evolution prepared us. Every crew member who has walked on the moon has pushed the boundaries of human experience into realms our ancestors could not imagine. Every long-duration resident of the International Space Station has contributed to understanding how human bodies respond to space, building knowledge essential for future exploration. The knowledge gained from these missions expands our understanding of both the cosmos and ourselves. We have learned things about human physiology through spaceflight that we could not have learned any other way. We have discovered capabilities we did not know we possessed, and limitations we did not know we faced. The technology developed for spaceflight benefits humanity in countless ways, beyond exploration, from medical imaging to water purification to materials science. But celebration should not obscure reality. Humans are biological organisms with biological limits. Those limits become starkly apparent in space, where every hour extracts a price that accumulates toward an eventual ceiling beyond which deterioration exceeds survival. The ceiling is real. It cannot be wished away through optimism or ignored through denial. It must be acknowledged and respected and worked within. The absolute limit of human survival in space is not a number of years that can be written in a textbook or a distance from Earth that can be marked on a chart. It is the point where cumulative biological damage becomes incompatible with continued function, where the body can no longer maintain the integrated operations that constitute life and health. That point varies between individuals based on genetics, conditioning, countermeasure compliance, and chance. It can be shifted somewhat through interventions that slow damage accumulation, but it exists for every human being and cannot be eliminated through any technology that preserves human biology. We are creatures of Earth. Our bones remember gravity through every cell that responds to mechanical loading by maintaining skeletal strength. Our eyes expect stable horizons and light cycles that follow predictable patterns. Our brains require day and night, social interaction, and the possibility of escape from threatening situations. Our cells can only absorb so much radiation before repair mechanisms are overwhelmed and mutations accumulate toward disease. This is not a limitation to be overcome, but a truth to be acknowledged about what we are and where we come from. The cosmos extends in all directions toward horizons beyond imagination. The survivability ceiling defines that reach with mathematical precision, written not in textbooks or mission plans, but in the structure of every cell that makes us what we are. The DNA that encodes human life also encodes human limitation. Both are part of the same inheritance from ancestors who lived and died on this planet long before any human dreamed of leaving it. Space does not care that we want to explore it. The universe will not modify its radiation environment or gravitational absence to accommodate human ambition. The biological constraints that define the survivability ceiling are as immutable as the speed of light and the arrow of time. They exist as properties of physical and biological reality, indifferent to human hopes or human planning. This is where human biology, not technology, sets the boundary. The boundary is real. The boundary is permanent within any time frame relevant to current planning. And understanding that boundary is the first step toward realistic engagement with humanity's future among the stars.